All right. So this is lesson two. So what I've done is kind of clumped together some lessons that I think would work well together and would work in the time of a class. So lesson one was all one group. Hopefully you could sit down and finish most of those. And now we're going to start lesson two. So lesson one was all about reaction rates. And lesson two is going to be about reaction dynamics. So you think about the word dynamic, it's meaning movement. So we are going to have the collision theory or the kinetic molecular theory, and then we're going to be looking at different aspects of that. So when you think about a reaction happening, molecules are these small little hard spheres that are constantly moving, even in a solid state. A reaction happens when there are collisions between these reacting particles and there's a transfer of energy. But not every time these molecules collide will there be a reaction. So not all collisions are successful. Every collision, and this is the two super important points, must have sufficient energy for a successful collision and be in favorable alignment. And we're going to be coming back to these two words sort of over and over again in this lesson. So the first concept I'm going to introduce to you is 1.5, which is kinetic energy and activation energy. Kinetic energy is the energy in a system due to the movement within the system. So, talking about this kinetic molecular theory or this idea that molecules are constantly moving. And the amount of kinetic energy varies depending upon the temperature of the system. But at a specific temperature, there will be what we call a continuous distribution of energy among molecules. Some particles will have low energy, some molecules will have high energy, and then most of the molecules will have intermediate energy. So if you look at this kinetic energy distribution table on the right, the y-axis says that it's representing the fraction of particles very close to the energy E. So this is going to be the number of particles, or they say fraction, but they kind of put different things. I like it when it just says number of molecules. That's kind of my favorite. And then the x-axis is going to represent the amount of energy that those molecules have. So if you look at here, in this distribution curve, so it's called a bell curve, right? So you've got very few molecules that have low energy. So this would be low energy. And then as you increase in energy, more and more molecules have more energy till you get to a place where you have the most probable energy. So that's where the most molecules have that amount of energy. And then there's average energy, which is a little bit past the middle. And then you again get to this right-hand side, which is similar to this left. So in the left-hand side, this was particles that had low energy. And then up here, these would be particles that have high energy. But what we're going to be making the connection to is you have to have enough energy for a successful collision to happen. So what we're going to have is what we call a threshold energy, or more specifically, an activation energy. It's the minimum or the threshold energy needed in a collision for a reaction to be successful or for a reaction to take place. A really great definition of this is the minimum energy colliding particles must have for a successful collision, because things can collide all the time. But when we talk about having a successful collision, it means that a reaction will take place. So on this diagram here, we would have our threshold or our activation energy, and then all of these particles to the right have sufficient energy for a successful collision. So every reaction has a different activation energy. If you have a lower activation energy, so something like this threshold here, so if you look at this line here, this is a lower activation energy than this one up here. So this lower activation energy means that more molecules will have sufficient energy for a successful collision, and the reaction will potentially be fast, right? There's just going to be more molecules with sufficient energy, so you're going to have more of those reactants colliding and producing products, so it's going to be a faster reaction. Whereas if you have a higher activation energy, that means that less molecules will have sufficient energy for successful collision, and the reaction will be slower. So, this is just a really nice short lesson just to introduce to you this idea of kinetic energy and activation energy. So, a question that I could ask you is which of the following has a higher activation or threshold energy, and what does that mean? So, if you look at this one on the left, this is actually a very low threshold energy. A lot of molecules, a lot of molecules have sufficient energy for a successful collision. Whereas on the right here, this is actually a very high threshold or activation energy. And you can do the short form for activation energy, which is energy with a subscript A. So it's an activation energy. Okay. And that means that this would be very few molecules have sufficient energy for a successful collision. Right? This one would be slow. This one would be fast. Okay. It's really good to write those sentences over and over again, right? It's just getting used to those sentences. Like it flows off my tongue when you talk about sufficient energy for successful collision. It's just kind of a slogan that you'll have for this entire unit. All right. So you can go and practice just a couple questions on this lesson.